Okay, this problem is asking how high must a satellite orbit above the Earth such that it remains at the same location above the Earth as the Earth rotates. So it will remain at the same height. This is called geosynchronous orbit. The question is, what is the height above the Earth at which geosynchronous orbit exists? So, in order to do this, the first thing we need to realize is that the period t is equal to 24 hours, the period of rotation. So we can calculate the velocity by going 2 pi r over t as the velocity in orbit. Now the r in this case is actually from the center. So we'll call this capital R and we'll call this a lowercase r. Now, the other thing which we need to realize is that we have centripetal motion here. Now, centripetal motion says that the sum of the forces that are centripetal is equal to the net force centripetal. Now, in this case, when we have a satellite going around, we're going to have a force of gravity that is going to be pulling towards the center of rotation, i.e. the Earth. So what we have is we have the force of gravity is equal to the mass times the centripetal acceleration. Now we do know that the force of gravity is equal to gmm over r squared, where the big M is the mass of the Earth and the little m is the mass of the satellite. And this m is the mass of the satellite. So we can replace that. We can say gmm Earth satellite equals mass satellite centripetal acceleration divided by r squared. Now we can then recognize that this mass cancels that mass, and we can also recognize that centripetal acceleration is defined as v squared over r, and we can thereby substitute in this value for that AC here. So it'll be g me all over r squared equals v squared all over r. Now if we multiply both sides by r, have I done this correctly? Yeah. If we multiply both sides by r, if I multiply an r on this side and I multiply an r on this side, this r cancels this r, and this r is going to cancel that. And therefore, I'm going to get gme over r is equal to v squared. I've done something wrong here, though. Let's just follow it through. I have a sneaky suspicion here. That's the force. That's the centripetal acceleration. Okay. Oh, I remember what I forgot. We can't leave v like this. We have to substitute in v equals 2 pi r over t. That's what I forgot. Okay. So if we do that, we're going to get 2 pi r over t squared equaling GME all over R. That makes better sense. Okay, now let's square this out. We're going to get 4 pi squared R squared over T. And now on this side we have the same thing. And we want to solve for R. And the way we're going to do that is we're going to take this R and put it up there. And we're going to take this T and put it over there, and take this and put it over there. So we're going to have G. Oh, yes, correct. Thank you. I made it. Forgot about the T squared there. So then we have G ME T squared all over 4 pi. Oops, that's not supposed to be there. And now we're going to have, that's going to all equal R cubed. So therefore, R is going to equal the cube root of GME T squared all over, oops, forgot the square on that guy, 4 pi squared. Okay? And that's going to equal R. So, let's plug in our values now and let's see what we get. A cube root of, let's move this over a little bit, 6.67 10 to the negative 11 times 5.98 times 10 to the 24 kilograms times, now this is 24 times 3,600 seconds per hour. That gives me seconds per day. Square that divided by 4 pi squared. And that R is going to be the, remember that R is the total distance from center to, from there to there. So in order to get it from the top, we're going to have to subtract the radius of the Earth. So we're going to have to go, big R is going to equal little r minus 6.38 times 10 to the 6 meters. That's the radius of the Earth. Okay? And that's the end of that problem. All you have to do is plug it through your calculator and take the cube root. Thanks for watching.